In this example, we solve a problem in which the soil is partially submerged. So here you can see a retaining wall with the parameters given here. H1 is equal to 2 meters, H2 is 3 meters. We have surcharge Q, which is 20 kilonewton meter squared. This is actually a distributed surcharge over a very large area, and we have the parameters for the soil. Gamma 1 is 15.5 kilonewton over meter cube, and gamma 2 is, which is gamma for the saturated part of the soil, is 18.5 kilonewton divided by meter cube. The soil is normally consolidated and OCR is equal to 1. The soil is granular with phi prime of 34 degrees, and definitely C prime would be 0 since the soil is granular. We should find at rest and active pressure distribution and also the resultant force. So we start with the at rest pressure. So K0 for a normally consolidated soil is 1 minus sine of phi prime. So it is 1 minus sine of 34 degrees, which would be 0.44. So we consider it at z equal to 0, z equal to 2, and z equal to 5. So at z equal to 0 we only have the surcharge load, and since this is a distributed surcharge, we just need to multiply K0 by this surcharge. So it would be 0.44 times 20, which is 8.8 kilonewton divided by meter squared. At z equal to 2, the soil is still dry, so we do not have any pore pressure, and we should multiply K0 by Q plus 2 times, which is H1 times of gamma 1, and it would be 22.44 kilonewton over meter squared. At z equal to 5, we are now under the groundwater level. So U would be, this is 3 meters. This was 2 meters. So 3 times gamma water, 9.81, would be the hydrostatic pressure, 29.43 kilonewton meter squared. And sigma prime H would be K0 times the effect of surcharge, everything from we have above z equal to 5 meters. So 2 times of the gamma of the soil, dry soil, and 3 times gamma prime, which is gamma sat minus gamma of W. This is gamma sat and this is gamma W. If you calculate this value, it would be 33.91. Now let's show them on a diagram. You can see here. So the blue one shows the distribution of the hydrostatic pressure, which is below the groundwater table, and this one shows the effect of surcharge. Here area 2 shows the effect of gamma 1, and area 3 shows the effect of surcharge and also the dry soil above H equal to 2, and this triangular, which is area 4, shows the effect of gamma 2, and which will be converted to gamma prime because the soil is submerged below H equal to 2. So to find the total force, we should find the area of these 5 sections. As you can see, A1 to A5. If you do that, you're gonna reach the value of 159.92, or approximately 160 kilonewton per meter and because this is a plane strain problem, and we define all of these in the unit lengths of the wall perpendicular to the surface of the problem you see here. And to find the resultant force from the bottom, so Z bar would be resultant force from the bottom. It should be somewhere here. So you should just take the moments of the resultant forces of each part, or actually the area of each part. So this one, which is 17.6, would be, so at the middle it would be 1 meter, and 1 meter plus 3 meters here would be 4. For area 2, we already have 3 meters, and 1/3 of distance from top to h equal to 2 would be 2 divided by 3, which is 0.67, plus 3 would be 3.67. And we have this triangle here. From the bottom it would be h divided by 3, which would be 1, and also area here, which is a rectangle. The distance would be 3 divided by 2, or 1.5. And also for the hydrostatic pressure, since this is a triangular distribution, the distance from the bottom would be 3 divided by 3, or h divided by 3, which is 1. And if you calculate Z bar, you should get this value, which is 1.77, actually from the bottom, not top. This is a typo here. So from the bottom.